Okay, so the first lecture is called Integrating Energy and Design. And what I'm going to do in this lecture is I'm going to talk through a case study project and talk about the integrated energy design strategies that were employed in this project. And the project is a school which I was the architect for, which was completed about a year ago. And we'll use that to demonstrate some of the principles and some of the approaches. So, integrated design. So first thing, who is involved? We talk about a design team. So we have a client, we have a design team, we have a contractor, we have specialists and subcontractors, and we have statutory inspectors who will inspect the work. So already in an architectural project, we've got a large number of people involved. CDM coordinator, this is to do with safety. And if we then look at the design team, on this project, the design team was an architect, which was me, quantity surveyor, who was in charge of managing costs, structural engineer, civil engineer, public health engineer, mechanical, electrical, sustainability consultant, lighting consultant, landscape architect, acoustician, ecologist, BREEAM assessor, interior designer, IT specialist, FF&E, that's fixed furniture and equipment, subcontractor specialists, and more. So, on this project, the design team was a whole range of people with different expertise. And I think it's important to understand, as an architect, that you always work with teams. And you have to understand where you can draw upon the expertise of other members of the team. Don't make the false assumption that the architect has to have all the expertise for all areas, because you don't. So this was a rendering of the school before it was built. It did change a little bit throughout the design process. The site was in Bradford, and we were working within a fairly tight budget. So there's not a huge amount of money spare. This was what we were aiming for. Very, very sort of solid, robust architecture using brick. Some shading devices to control the overheating on the south facade, and some optimization of the windows in terms of providing the correct amount of window area to the rooms behind. So, site parameters. Orientation. That was our site, and that was our kind of diagram of the site. So there are many site factors coming into play here, and that led us to look at this linear orientation for the building. And the important thing environmentally, which we touched upon this morning, is that in the UK and in the northern temperate zones, your south facade, ideally, your main facade is orientated south. Okay, so it's facing south. Or if you can't, try to get it within 30 degrees of south. You will then be starting with a much more controllable situation in terms of solar control and daylighting. Now, we were lucky on this site because we could orientate the primary facade facing due south, which was the absolute ideal. We then also have another facade facing north, which is also a kind of optimum situation for this type of building. And that was a slightly developed site drawing showing the building here. And you can see this is just a drawing, just drawn by hand. This was my drawing. Early on, early stages in the project. We were just exploring layouts on site. There's no need to start building very time-consuming computer models. We're just doing some quite quick drawing to get a feel for things on site. So, looking at that orientation that we talked about. Now in this lecture we have a mixture of images and graphs. And what you probably will need to do is re-watch the video, look at the slides again to fully understand all of these graphs. Okay? And what we will typically be doing is we're looking at a 3-day period in summer, 30th of July through to the 1st of August. And we are looking at different parameters, which in this case is the room temperature. So, if we put the first line on, which is the outside air temperature. So over that 3-day period, our scale here starts at 22. Okay, we're not too interested in anything below that because we're looking at overheating. So the outside air temperature, it rises during the day to 28, drops down again at night, rises the following day, drops down again, rises on the 3rd day, but this time it's getting warmer, up to about 30 degrees. So we have a hot 3 days. If we now put our east facade in this pale blue line, it looks sort of green. It's green on there, doesn't it? It looks blue on my screen. In fact, it's hard to tell now if that's the south or the east. I think it's meant to be the east, but we'll find out in a moment. South, isn't it? Yeah. It's definitely green on there. And on my screen it's sort of blue. Okay, south then. So now we're looking at the internal temperatures on the south facade. So inside, we drop down at night to about 22. It peaks during the day, drops down again, peaks on the 3rd day, drops down again. If we now put our east, east, and compare it with the south, it's not performing as well. So we're getting hotter temperatures on the east. If we then put our west, you see that the west facade is performing the worst. So we're peaking up here in the sort of 31 degree range, and at night we're only dropping down to about 26, 27. So that's a kind of overview of that west facade. And as we mentioned this morning, the problem is that the west facade, it's very difficult to block out the sunshine. Now if we just go back quickly to my site plan, by optimizing our orientation, our west facade is tiny. And in fact, that west facade didn't have any windows in it. So we're minimizing the problem facades, we're minimizing. So it makes it much easier to design. Now obviously, on some sites, you don't have any choice of orientation. Okay, let's just go on to the next one. So, the influence now of orientation and window area on heating load. So we're looking at north, east, south, west and north again, and we're looking at these two different comparisons, 70% window and 30% window. And this is the heating demand. So this is now not looking at the problem of overheating, it's looking at winter to say how much heat do we need to provide. So if we have 30% windows, as you might expect, we provide less heating on the south, and we need to provide a little bit more heating on the north. And if we go for a higher glazed proportion of 70%, we need to provide more heating, particularly on the north. Okay. Now the reason for this is quite simple, because the performance, the insulation performance of windows is not nearly as high as a wall. So in our climate here, when you put more windows in, you start to lose heat through those windows in summer. But what is interesting is on the south facade, the difference is fairly small in terms of how much heat you need to provide in winter. On the south facade. And I mean, the reason behind that is fairly obvious, that in the winter months when you're providing heating, you will be catching some solar gain on that south facade. So, now we're looking at the same again, but we're now looking at spaces with high internal heat loads. So spaces that have a lot of heat sources, and which the example here is 50 watts per square metre. Now if you think you're each currently giving off about 100 watts of heat, so we've got quite a lot of heat sources in this room. If we had some computers, we'd have more. So, this is a good example probably of a high internal heat load. And you might notice when you, if you come into one of these lecture theatres after a lecture has just finished, it's quite warm because everyone's been heating up the space. So if we compare now, with our 30% window, we're barely providing. We don't need to provide a lot of heat because we're providing the heat ourselves, but there is some heat provided, mainly in the north. And if we look at our 70%, again, the difference becomes much less. Okay? So it's a big difference that between a space which has high internal heat loads or a space which has no internal heat loads. When you move to spaces with high internal heat loads, you become much more concerned with keeping them cool enough. Okay, and that's the comparison there with the normal heat load. So you can see that the difference in the amount of heat that you have to provide is quite substantial. Okay, moving on to acoustic design now. That's a bit blurry, but this was an image of the acousticians doing an acoustic survey of the site. And this is very similar to what you were doing last Friday, where you were doing it with your mobile devices. The acousticians are using a slightly better piece of equipment, but the same idea. They're going around the site and they're taking acoustic readings. And what they then do is they put that into a computer program which takes those point readings and it starts to simulate the acoustic spread across that site. And if we just look at it, this is a road, and the red is clearly giving us the higher noise levels, and then it reduces down, but critically, for a lot of the areas adjacent to the building, we're in about 45 decibels, okay, quite a high noise level. And the implication for this project, because it's a school, is we have to comply with these sound levels. And the key factor here is we have to provide an internal ambient noise level no greater than 35 decibels. So, as a rule of thumb, when you open a window to let air in, you reduce the noise outside by about 10 decibels. So what this told us, if we go back, this region on site, which is experiencing about 45 decibels, is unlikely to meet the acoustic criteria if we open the windows for natural ventilation. Okay? So that's really critical. Very early on in this project, the acoustics of the site are starting to define the principles of ventilation, the principles of the facade, and even the principles of the structure of the building. Okay, so there's just highlighting our 45 dB. And this is our mechanical engineer then also doing a further analysis to decide which rooms would need mechanical ventilation, either to meet the acoustic requirements or because those rooms have functions that need mech vent. So for example, a kitchen will need mechanical extract, a woodworking room will need mechanical extract. And what we were left with is a scenario where most of the rooms within the building would need to be mechanically ventilated. Now, generally, in the UK, your first choice would be natural ventilation. If you can make it work, it's generally the most efficient, most low-carbon means of cooling and ventilating a building. But we were faced with a situation here where we could not make natural ventilation work. So the environmental strategy, which led on from that, was we did these kind of sketchy drawings to explore that, and what we were looking at was a whole series of interventions. We're keeping natural ventilation in this kind of atria space, but all the other rooms are mechanically ventilated. It's a bit small to see there, but what we're looking at is heat recovery and nighttime purging. And I'll come back to that in a moment. Okay? That's just a close-up. And I'd recommend it for your design projects. This kind of environmental strategy drawing is very helpful for capturing the principles of your design. That's a bit blurry, I'm afraid, but that was this is just an extract from the Revit model showing the implication of the mechanical ventilation route. So everything you're seeing on there is ductwork for air. Okay? So the building is then completely full of ductwork. The issue about mechanical ventilation is because you need to move a lot of air about, you need very big ducts to push that air through the building. Sorry, it's a bit blurry. Okay, thermal mass. So what we mean by thermal mass is when the materials in the building have a high specific heat capacity. So those materials are able to store a lot of energy. So to give you some examples, the floor that I'm standing on is made of concrete. That will absorb a lot of heat, a lot of energy. That plasterboard wall, which is hollow, will not store much heat. That is a plasterboard ceiling, so that will not store much heat. Before the Arts Tower was refurbished, that was a concrete ceiling, and that would store heat. So we're looking at elements of the building that can store heat. And if we look now at the implications of that, so we have our same graph that we used before. The black line is the outside air temperature. And we'll put on, first of all, our light mass. So lightweight construction, this kind of stuff. All right? So we're saying that that building is predominantly made with light construction. And the temperatures in that building are peaking up. They're going up to 30, down again, up to 32, down again, up to 32. So we're typically getting internal temperatures that are hotter than the outside air temperature. And 32 degrees is not a comfortable temperature. If we now put on our medium mass, which is the red, so medium mass would mean a construction where you probably have concrete soffits and a concrete floor. And already you can see the significant benefit. Those internal temperatures are now lower than the outside temperature. So when it's 30 degrees outside, it's 28 degrees inside. So the thermal mass is giving us that benefit. And if we now switch on our heavy thermal mass, and heavy thermal mass would mean ceiling, floor and walls are heavyweight, and you get this huge improvement whereby your internal temperature might be 25 and your external temperature might be 30. So you're getting this huge benefit, and it's a very, very effective passive sustainable design approach. Passive, because it's not doing anything. Your building needs a structure, it needs a floor, and it's not, it's got no controls, it's just a big lump of concrete, making a huge difference. Okay. I need to go back to that slide. The important thing with this is that we're talking about nighttime purging as well. And what we mean by nighttime purging is simply that at night, when the outside air temperature is cooler, we either open the windows or we use the mechanical ventilation to bring lots of that cool air in all throughout the night to cool down your thermal mass. Again, very effective passive technique. So this led us on to look at some structural strategies because we knew we needed that thermal mass. And these were the 4 options that we looked at. So on the left is a steel frame with concrete precast planks and a concrete topping. Option B is what's called slim floor, whereby your steel beam has this extra plate welded onto it, allowing you to sit your concrete planks onto that extra plate and to give you a much thinner floor slab. The voids here is where your structural engineer can define where you don't need to have concrete, and we could put some polystyrene fillers in there so that we need less concrete. Option C is a reinforced concrete flat slab, and option D is a slightly thicker reinforced concrete flat slab. Now on this building, for various reasons, we ended up going for option B, but that was quite effective because it gave us our concrete finish and it also gave us quite a thin floor slab. If we'd gone for option A, bearing in mind that we've got to get all those air ducts underneath our structure, would have given us a very, very deep floor. Whereas with option B, we can run our ducts directly underneath. That's an image of the precast concrete planks. Then we put the insulation goes in, the polystyrene, and then the concrete is poured on the top. So that's I don't know why that image is so bad, but that's the concrete soffit. So you can just about see it. We expose that concrete underside of the slab. And again. Okay, exposed concrete up there. And that was an image of the main steel work in the building. There's quite a lot of steel work. This was a completely Revit built project, so it's very easy to look at the structure independently. That's another blurry one, not sure why that is. This is another different project, but I just thought I'd throw this in to give you another example of concrete thermal mass. This was a project I worked on many years ago, and the same principle of exposing that concrete to get that thermal mass. And a different project here, but again, these are concrete soffits to give you that thermal mass. Okay, influence of air change rate. So we have our same sort of graph here, and we're looking at 3 different air changes. So we're looking at 1, 1.5 and 2 air changes per hour. An air change per hour is, if you imagine this room, all of the air within this room would be replaced within 1 hour. And if we look at our heating load, that's the 1 air change per hour, 1.5 and 2. So unsurprisingly, the more air you need to change, the more heating you need in your building. Now if we compare that again with our high internal heat load, so the kind of room we're in with all of us giving off heat, you need significantly less heating. And again, as we mentioned before, the buildings with the high internal heat loads, keeping those buildings warm is very easy. It's keeping them cool which becomes the problem. Okay, influence of passive preheat on incoming air. So what we're meaning here is, rather than bringing the outside air straight into your building, we provide some heating to that air through a passive means. And I'll show you some examples in a moment. But now we're looking at the same graph, but we are preheating the incoming air. And there's quite a significant reduction in the amount of heat energy we need to provide. So, earth tubes were the strategy that we were using on this project. And an earth tube is very simple. It's a big concrete pipe in the ground. So you bury these pipes. They have to be quite long. They're typically about 1.4 to 1.6 meters diameter. And you have an inlet, which on this job was disguised as a seat. So the air comes in through that inlet. It's pulled through the earth tube with a very low-powered electric fan, and then it pulls it into the building. That was our engineer's layout of the earth tubes. Now what you're doing is, when you pull the air in, as it is passed along that concrete pipe which is buried in the ground, in winter it's getting gradually warmed up by the earth, and in summer it's getting gradually cooled by the earth. So it is a fantastic means of getting some free heat in winter and some free cool in summer. We have this term cool, meaning the opposite of heat. But it means basically getting some free cooling in the summer. It's a very, very good system. You do need to have quite long pipe work. So it would not always be possible in an urban situation. And also, you need to bear in mind, where are you going to draw the air in? So you need to be pulling in clean air. So it would be no good if you were pulling in air from, for example, adjacent to a road. Okay, heat recovery. Heat recovery is talking about systems whereby, rather than ventilating by just letting the air in this room go outside, you're trying to recover the heat from that air. So at the moment in this room, we provide heat through these radiators, and then because we want ventilation, we open the windows, so all that heat goes out the window. Okay? So it's a real, really daft system. We're then warming up the planet even more. We need to put more heat in because we're putting all that heat out the windows. Heat recovery says, let's capture the heat from that air. We have to get rid of that stale air, but we want to take the heat out of it first and put that heat back into our fresh air. So if we look here at the example, this is the same graph comparing our heating load. So without heat recovery, it looks like that. With heat recovery, you're getting a sort of 15 through to 30% energy saving on your heating. Okay, nighttime purging. We talked about that briefly, but a little bit more detail here. So nighttime purging is, we're talking about getting rid of the heat within your building at night. So we're looking at our 3-day period. That's the outside air temperature. And we're going to look at a few different air change rates. So if we look at green, 2 changes per hour, we are making an improvement on the outside air temperature. If we then go to 4 air changes per hour, the improvement is greater. And if we go all the way through to 8 air changes per hour, we are making a significant improvement in thermal comfort, to the point where if you take this 1st of August, which is probably the hottest day in the year, outside it's 30 degrees, inside it's just over 26 degrees, which is just about comfortable. And you're doing this simply by cooling the building down at night. Okay, daylight. So daylight is very important in schools, and you have to meet the daylight criteria. And I've kind of mentioned this before, but this was probably 3 years ago now, at a point when architects were not able to do daylight analysis, and so we had to send our daylight analysis over to the engineer. But the principle is, anyway, that the engineer is simulating the daylight, and we're able to start to optimize the facade. And that was that's one of the views inside, where we managed to get these very good window sizes. That's our concrete soffit up there. So window proportion. Again, we've got our 3-day period, and we're going to look at a few different window areas and to see how that affects the overheating. There's our baseline, that's the outside air temperature. And the green is if we have 30% glazing. Okay, so 30% glazing, we are able to keep the inside temperature relatively cool. If we then go through the different percentages, what you can see is that typically the more window area you have, then the hotter you will make your internal temperatures. But of course, this is not including shading. If you can manage to increase your window area, but also develop a shading strategy, you can take that back down to the much lower level. But this is why, even in the UK, you need to think very carefully about shading your windows, or you can end up with overheated buildings. So we looked at some solar screening, and here what we're looking at is comparing internal and external shading and looking at an interactive shading system. So we'll go through that. The black is our outside air temperature, and the blue is the effect of internal shading, so this kind of stuff here. And it's not very effective. Okay, the internal temperatures are higher than the outside temperatures because you've let the heat in. The heat's come through the glass, it's in your building. Not effective. If we now look at the fixed external screening in red, much more effective at controlling those internal temperatures. And then if we look to the last one, the green one, is an interactive screening. So what we mean by that is that this is a shading device, or louvers, which can manipulate depending on the sun intensity. And in this example, it's a system which is controlled so that when the sun's intensity increases more than 180 watts per square meter, that shading device will close down. And as you can see, this is by far the most effective system. So it's something to bear in mind in your design projects, that if you think you can justify it, you can afford it in your project, some kind of interactive shading device will perform the best, because it can manipulate itself depending on what the sun is doing. Any fixed shading device obviously can just stay in the same place, and it will be like that in winter or in summer. And these were some of the initial shading studies we were looking at. We then moved on to this device, which what you can see is it's shading the high sun in the south, and we've got this extra panel which is trying to shade that difficult west sun. And we have no shading on the east, because that eastern sun is not so much of a problem. And that's the actual built project. So that's that side panel, and in the end we had these kind of timber louvers shading the top of the window. Okay, so looking at some other solar screening strategies. We've got our outside air temperature, and the first one we're looking at in blue is no screening at all, just glass. If we then look at solar controlled glass, so this is glass which has special coatings to reduce the solar gain. Solar controlled glass is actually quite effective. So if you can't manage to get any shading into your building, solar controlled glass will help. But better is a shading system showing the green line. In this case, it's a screening system which is operated by the internal temperature of the room. So when the room exceeds 24 degrees centigrade, that solar screening system will close down. Okay, that's just an image inside showing these are acoustic absorbers which just absorb some of the sound in the space. Okay, and that's our concrete soffit which we painted white. Just a few more images inside the building. These are the acoustic absorbers again. We've got a high level atrium which allows the heat inside to rise and to dissipate through these top windows. You can probably just make out all of these walls have got perforated holes here. That's all acoustic absorbent materials, because in a school you've got hundreds of school children making lots of noise, so you need to absorb some of that sound energy. And that was the similar image. Okay, so we've just got an example now, which is JSWD Architects in Cologne. I've just got a few images of some of their work. This is an interactive screening device, which you can sort of make out on these facades here. So this shading device is activated. I think there's a closer view, yeah. So that there are sensors sensing the internal temperature in those rooms. And at the moment when that temperature reaches a certain point, these shaded blinds drop down and block out that overheating sun. And you can see the kind of effect you get when some of the blinds are down, some of the blinds are up. Okay. And this is a much simpler example where it's user controlled. So we've got these screens and they can slide. Okay, and it's just down to the occupants of that building just to decide to slide those screens over if they want a bit of extra shading. And this is a really interesting project, which has a much more complex screening system. The entire building, it's an office type building, is covered with an interactive screen. And I've got some close-ups of that. That's what it looks like. And it's a really kind of amazing system which it can manipulate itself depending on the intensity of the sun. It's shading the glass, but it's still allowing views out. It creates this really sort of interesting facade, I think. That's what it looks like. So at close-up, I think it's aluminium louvers. And this is, I think, really important, that whenever you're shading or providing screening, you need to consider the impact on the interior space. And I think what this is showing is that even when that screening is closed, you're still getting very good views out of the building. Now, the difference, I'm using the terms shading and screening. We tend to talk about shading as a kind of discrete shading device on a window. Screening is more this, where the entire window is covered with a screen. This is much more effective at controlling solar shading. It's also much more expensive, and any of these systems which have movable items, there is a maintenance cost. You have to make sure they keep working. That's a view at lower level. I think there's a detail, yeah. So this is the system, and the same screen is applied to all facades, north, south, east, west. They all get the same screen. Now I'll go back a bit, which I suspect is because the architects probably wanted a kind of uniformity of appearance across this building. So the basic screen is the same. They also get some efficiencies of economy in that they're making thousands of the same device. If we go back to the diagram of operation, very clever system. Depending on where the sun is, a facade can be shaded to block out a sun from this direction, or it could be shaded to block it out from more in the west. It could be fully closed, so you'd be getting some light through that screen, but it's fully closed in terms of shading. Or it could be blocking out the more sort of easterly, or it could be blocking out the morning sun. And every facade is able to manipulate itself to optimize the daylight and the overheating of those spaces simply by pivoting about this central axis point. So I think it's a really, it's a really interesting example. Okay. So when I issue these slides, the reference is on there. If you type it into Google, you can find there's a lot more information online about this project. Very, very good project. That's the sort of elevation and the plan here, showing how that looks, looking down on it. And there we see kind of three different phases, I guess, where we've got it fully closed, partially open, and then I think a little bit more open over here. And this is all computer controlled. Very, very interesting project. Okay. Anyone got any questions before we break?